with some basics in place on straight lines, with which I'm assuming you've bred semblance of familiarity and you are friendly with those ideas already. I want to just add a few more things as part of our concluding conceptual remarks on straight lines. Problem solving, of course, remains pending. We're going to take on to problem solving once I'm done with this last bit of straight lines in terms of concepts. So, the first thing that I want to deliver to you is knowledge of an expression of this kind. Ax squared plus 2hxy plus by squared. What is this? This is an expression, isn't it? It's only an algebraic expression. It's dumb. It has no value associated with it. It will take the value that you want it to take, right? You can assign different values to x and y, and this expression will assume different values commensurate, right? But what is special? I'm assuming a, h, and b are constants. X and y are variables, and you could assign different values to these variables, right? This was therefore a function of x and y. It's an expression in x and y. Now, what's special about this expression? What's special about this expression?
It's a mixture of two equations. It's a mixture of two equations.
Equations. An expression is never a mixture of equations. These are different paradigms. There is no equation associated with it. This is just an expression. Can you tell me what is special about this expression? Yes. Look at, where is that parabola coming from? Come on, let's. See, the important thing is, look at the first term, ax squared. This is ax squared into y to power 0. If you add the powers of x and y, it's 2. Yes or no? Look at the second term, 2hxy. If you add the powers of x and y, it turns out to be 2. Right? Look at the third term, by squared into x power 0. If you add the powers of x and y, it turns out to be 2. So the three terms are homogeneous in the context of the sum of the powers of x and y adding up to the same number. So the expression, therefore, since the sum of the powers of x and y add up to the same number, is homogeneous in character. And since the sum of the powers is 2, this expression is called a homogeneous second degree expression in x and y. This is referred to as a homogeneous second degree expression in x and y. Every term is of degree 2. Every term in this expression is of degree 2. If the sum of the powers of x and y add up to 3, then that's going to be a homogeneous third degree expression in x and y. If the sum of the powers of x and y for each term add up to n, then it would be a homogeneous nth degree n expression in x and y. Right? This is a homogeneous second degree expression in x and y. It has no geometrical consequence. It's only an expression. You say x is 1 and y is 3. What's the value of this expression? You say x is minus 1, y is 2. What's the value of this expression? This expression will assume different values for different values of x and y. Clear? Now, having said this, there are certain set of x and y's. There are certain xy pairs that will cause this expression to be 0. Isn't it? Not every set of x and y will cause this expression to be 0. There are certain special xy's that will cause it to be 0. This expression will be rendered 0 for certain pairs of x and y. Right? Those xy's that cause this to be 0, if they are joined together, those xy's that cause this to be 0 when they are joined together, they constitute a curve. That's called a homogeneous second degree curve in x and y. That's called a homogeneous second degree curve in x and y. You know, all those xy's, there are different xy's that will cause this to be 0. Now if you join all those xy's that will cause this expression to be 0, then the curve thus obtained is called a homogeneous second degree curve in x and y. Right? That means this was just a homogeneous second degree expression. This is a homogeneous second degree equation in x and y. This is a homogeneous second degree equation in x and y. Right? An equation is an entity which is true for not every set of xy's, but which is true for some set of xy's. Right? Not every set of xy's. So all those xy's that will cause this to be 0 belong to a curve which is called a homogeneous second degree curve in x and y. The question then is, there is a geometry associated with this curve, therefore there is a geometry associated with all those xy's that cause this to be 0. We will then embark on mission finding the geometry of such a second degree curve, such a homogeneous second degree curve. What does it geometrically represent? That's the mission. Right? Now, let's obtain the geometry associated with a homogeneous second degree equation in x and y. Let me divide throughout by x squared. Let me divide throughout by x squared. What then? And start writing from this last term onwards. B into y by x whole square. B into y by x whole square plus 2h into y by x, right, on dividing by x square, right Chirayu, plus a is 0 on dividing by x squared. This is what transpires. Clear? A, h and b are constant entities, are fixed numbers, right? This then is like some bt squared plus 2h into t plus a equal to 0. This is what this is. Where t is y by x. Where t is y by x. This then is a quadratic in y by x. T is y by x. This is a quadratic in y by x. T is y by x, right? It's a quadratic. So when you solve for t, that means you are essentially solving for y by x, right? When you solve for t from this quadratic, you are essentially solving for y by x. So this quadratic in general will give me two roots, m1 and m2. m1 and m2. That means when you solve for t, that means you are solving for y by x, you end up getting two values of y by x. Y by x could be m1 or y by x could be m2. Y by x could be m1 or y by x could be m2. Where what are m1 and m2? m1 and m2 are the roots of this quadratic in y by x. Right? Right? Now, sum of the roots would be m1 plus m2, which is minus 2h by b would be the sum of the roots of this quadratic. All of you understand sum of the roots and product of the roots, right? So m1 plus m2 is minus 2h by b. The product of the roots is a by b. Right? No issues with this. No issues with this, right? Which means now, when I obtain the value of y by x, I get two values, m1 and m2, which gives me one of the possibilities as y equal to m1x. If y by x is m1, then y will be equal to m1x, or I get y by x equal to m2, that gives me y equal to m2x. That means the consequence of this is going to be either y equal to m1x or y equal to m2x. But what is y equal to m1x? A straight line passing through the origin having slope m1. What is y equal to m2x? Another straight line passing through the origin and having slope m2. That means this then represents what? Two lines, y equal to m1x and y equal to m2x, passing through the origin and having slopes m1 and m2. That means a homogeneous second degree equation in x and y in general. A homogeneous second degree equation in x and y in general represents a pair of straight lines passing through the origin. This is the pair of straight lines passing through the origin with slopes m1 and m2, where m1 and m2 are the roots of this quadratic in y by x. Does it make sense to you or not? So then, the geometrical interpretation of the second degree equation in x and y, the homogeneous second degree equation in x and y, the homogeneous second degree equation in x and y represents a pair of straight lines passing through the origin, y equal to m1x and y equal to m2x is a pair of straight lines passing through the origin. If this angle is theta 1, then m1 would be tan theta 1. If this angle is theta 2, m2 would be tan theta 2. Yes or no? Right? Where the roots would be the slopes of the two lines. The roots of this quadratic would be the slopes of the two lines represented by this homogeneous second degree equation in x and y. Yes or no? Now, if I have to find the angle between, first of all, the two lines that I obtain out of this homogeneous second degree equation may or may not be real. They will be real if m1 and m2 are real, then these lines would be real. But if m1 and m2, the roots of this are imaginary, then the two lines that we are conceiving of are imaginary lines or complex lines, right? So, in a general sense, mathematically we say it does represent a pair of straight lines passing through the origin. It's another story whether those lines are real or not, right? Now, when would those lines be real? Lines would be real if m1 and m2 are real numbers. If m1 and m2 are real numbers, then the two lines would be real lines, right? And when would m1, m2 be real? When the discriminant of this quadratic is greater than or equal to 0, then the lines will be real, right? That means discriminant greater than or equal to 0 for this quadratic 1, because m1 and m2 are the roots of this quadratic. Its discriminant has to be non-negative for m1 and m2 to be real entities, right? And this would mean 4 into h squared minus ab to be greater than or equal to 0, right? Right? Then the two lines that this represents are real lines, right? Now, if as a special case of this, if discriminant is equal to 0, that means h squared would be equal to ab. Then the two roots would be equal and real, the two roots would be equal and real, coincident roots of this quadratic. That means this will cause m1 to be equal to m2. This will cause m1 to be equal to m2. And if m1 is equal to m2, the two lines represented here would be coincident lines. Two lines passing through the origin having the same slope must be coincident real lines, must be coincident real lines. That means if h squared is equal to ab, what does this represent? This represents a pair of real coincident lines, coincident real lines, right? If discriminant is greater than 0, that means if h squared minus ab is greater than 0, that means if h squared is greater than ab, then m1 and m2 would be distinct and real, would be distinct and real. Would be real and distinct, right? If m1 and m2 are real and distinct, then the two lines would be real and distinct. So this gives me, if h squared is equal to ab, this gives me a pair of coincident real lines. If h squared is greater than ab, I get a pair of distinct real lines. I get a pair of distinct real lines out of this homogeneous second degree equation in x and y. Clear? Now if h squared minus ab is less than 0, that h squared minus ab less than 0 means discriminant will be less than 0. m1 and m2 would be imaginary, and lines are imaginary. Yes or no? Okay, good question. Real lines are something that you can conceive of. Imaginary lines in the context of what we are studying are something that you can only imagine, right? So yes, see, not everything will find a geometrical way to look at things. So this time these are some lines, semblance of lines, some entity passing through the origin, but you can't represent it in the real Cartesian plane. So we call them, see, square root of -1, for example, So can you conceive that? So when you can't conceive that, you say, all right, I'm going to, this opens the Pandora's box for me, and now I'm going to conceive a new set of numbers with a new idea, a new paradigm, a new dimension, and I will write everything in terms of square root of -1, which is I. Yet, I have to tell you, too early to talk about that right now, but I promise to come back to it when the time is right, when you have grown up a little more. I will be able to elaborate a little more on, what exactly are these imaginary lines. It's not that, I'll be able to plot them in the xy plane, but I would be able to give you more insight when the time is right. Okay? Now, for the time being then, h squared less than ab, h squared less than ab will give me imaginary lines out of this homogeneous second degree equation in x and y. One way or the other, this will always represent a pair of lines, be it real and coincident, which happens when h squared is equal to ab, be it real and distinct, which would happen if h squared greater than ab, or be it imaginary lines, that's going to happen when h squared less than ab. Clear? Now, can I remove the clutter from here? Right? Now, say if h squared is greater than or equal to ab. That means lines are real. Lines are real. Discriminant greater than or equal to 0 means lines are real. And if the two lines are real, One would be of slope m1. The other one would be of slope m2, where m1 and m2 are connected as such, sum of the roots and product of the roots. Now, if theta is the acute angle between the two lines that this represents a pair of straight lines. If theta is the acute angle between these two lines with slopes m1 and m2, then what is tan theta going to be? m1 m2, mod of m1 minus m2 by 1 plus m1 m2, right? Right? Now, so m1, m2 I already know, it's A by B. I need to find the value of mod of m1 minus m2. Now, can I find the value of m1 minus m2 whole square? How? Right. m1 plus m2 whole square minus 4 m1 m2. Right? So m1 minus m2 whole square is going to be m1 plus m2 whole square minus 4 m1 m2. m1 plus m2 whole square minus 4 m1 m2, right? But what is m1 plus m2 whole square? 4h squared by b squared. 4h squared by b squared. Minus m1 m2, which is a by b. Yes or no? Which is 4 into h squared minus ab by b squared. That's m1 minus m2 whole square. And therefore, what's going to be? If I take the square root of m1 minus m2 whole squared, what will I get? If I take the square root of both sides, then what will be the square root of m1 minus m2 whole squared? Can you tell me, please? Huh? Tell me this. Mod of m1 minus m2. Root x squared is not x. Root x squared is mod x. Mod x. Always. Root x squared is mod x. Will you forget this ever? Except when you know that x is non-negative, then you can say root x squared is x. But if you are unsure of the sign of x, rest assured, root x square will always be mod x, not x, not x. Right? So, root m1 minus m2 whole square is going to be mod of m1 minus m2 is going to be mod of m1 minus m2. Yes or no? So, what I do is, my objective is to find mod m1 minus m2, the numerator of this. So, if I extract the square root, then the left hand side would be delivered to me as mod of m1 minus m2. Right? So, from this, on extracting the square root of m1 minus m2 whole square, I end up getting mod of m1 minus m2 equals 2 root h squared minus ab by mod b. Root b squared is not b. Look, I just told you, don't forget this. If I take the square root of b squared, it's going to be mod b, not b. Only if you are sure that b is a positive number, go ahead and claim it's going to be b. Otherwise, it's going to be mod b unconditionally. So, 2 root h squared minus ab by mod b. Right? My objective is what? To find tan theta, tan of the angle between the two lines that this represents. Tan of the angle that between the two lines that this represents. That's the objective. That's the agenda. Right? So then, tan theta is going to be mod of m1 minus m2, which is this, 2 root h squared minus ab by mod b divided by mod of 1 plus m1 m2, mod of 1 plus m1 m2, mod of 1 plus, what's m1 m2? m1 m2 is a by b. Right? Which then reappears as, can I remove the clutter from here, this portion? Tan theta is 2 root h squared minus ab divided by, this mod b comes down here, it will become mod a plus mod b. I'm sorry, mod of a plus b. It will become mod of a plus b. When this mod b comes in the denominator, it's going to become mod of a plus b. Right? That's the tan of the acute angle between the two lines that this represents. And very clearly, for the two lines to be real, the tan of the acute angle between them has to be real, and that can happen only if h squared is greater than or equal to ab. The two lines would be coincident if theta is 0. That means when h squared is equal to ab. And not only that, realize that if tan of the angle between the two lines is undefined, then theta must be 90 degrees. If tan theta is undefined, theta must be 90 degrees. Yes or no? So when would tan theta be undefined? If a plus b is 0. If a plus b is 0, tan theta would be undefined. So then, if theta is 90 degrees, that means if the two lines are perpendicular to each other, a plus b has to be 0, isn't it? That means coefficient of x squared plus coefficient of y squared must be 0. What is a? A is the coefficient of x squared. What is b? Coefficient of y squared. That means coefficient of x squared plus coefficient of y squared must be 0. For the two lines to be perpendicular. Coefficient of x squared plus coefficient of y squared must be 0 for the two lines to be perpendicular to each other. That means a must be equal to minus b. You could also see that from here. If the two lines are perpendicular to each other, m1, m2 must be minus 1. Right? If the two lines are perpendicular to each other, then m1, m2 must be minus 1. That means a by b must be minus 1. That means a plus b must be 0, which is what we expected, right? So for two lines to be perpendicular to each other, if this represents a pair of perpendicular lines, then if a is 3, b must be minus 3. The algebraic sum of a and b must add up to 0, then it will guarantee a pair of perpendicular lines. If h squared is equal to ab, what will produce is a pair of coincident real lines. If h squared is less than ab, this will produce a pair of imaginary lines. One way or the other, the angle between the two lines is given by 2 root h squared minus ab by mod of a plus b. Is the idea clear or not? Right? Now, having said this, so far so good, right? Doesn't bother you? Now, so this, let's say for h squared greater than ab, represents a pair of real lines. Pair of real lines. If h squared greater than ab, a pair of real distinct lines, right? With slopes m1 and m2 given by this. Clear? Now, there is a line with slope m1. There is another line with slope m2. This is what this represents. There is this origin O. Now between these two lines, there would be a pair of angle bisectors, and that pair of angle bisectors will always be perpendicular. Between any pair of lines, the two angle bisectors are always perpendicular to each other, right? So, let's say this is one of the angle bisectors between the pair of lines. This pair of lines represented. So this is essentially a compact way of representing a pair of straight lines passing through the origin. This is only a compact way of representing a pair of straight lines passing through the origin, right? And between the two lines that this represents, there would be a pair of angle bisectors. This would be one angle bisector, and there is going to be another angle bisector, and those two angle bisectors would be mutually perpendicular. So now this was the combined equation of a pair of lines. I want to now find the combined equation of the pair of angle bisectors of these lines. You know what I'm saying? These two lines are a pair of lines represented by this. This is a compact way of representing this pair. I want to find the compact representation of a pair of the pair of angle bisectors of these two lines. You know what I'm saying? And of course, the two angle bisectors will also pass through the origin, right? The two angle bisectors between these two lines will also pass through the origin. So that will also be a pair of lines passing through the origin, and that therefore will also be represented by a homogeneous second degree equation in x and y, but a different equation. This is one homogeneous second degree equation in x and y. The pair of lines that are angle bisectors of these will be another homogeneous second degree equation in x and y. And what I am guessing is the homogeneous second degree equation in x and y that will represent this angle bisector would be such, will be such that the coefficient of x square in that plus the coefficient of y squared in that will be 0. Why? Because those must be perpendicular lines. Yes or no? Right? Okay. Now this is, say, one of the angle bisectors. This is, say, one of the angle bisectors. Clear? This is theta 1. This is theta 2. And this is the angle bisector. This is theta. For the angle bisector, the slope is tan theta. The slope is tan theta for the angle bisector, right? Now, can I say, if this is the angle bisector, can I say, not say that theta must be theta 1 plus theta 2 by 2? Can I say this? The angle that the angle bisector makes is theta, and that must be theta 1 plus theta 2 by 2. This is exactly angularly halfway between the two lines, right? 2 theta must be theta 1 plus theta 2. Right? Where m is the slope of the angle bisector, tan theta, right? The slope of this angle bisector is tan theta, right? Tan theta is the slope of the angle bisector, right? Now, if there is any point P x comma y on the angle bisector, if there is any point P x comma y on the angle bisector, then what would be the equation of the angle bisector? It would be a relationship that would connect the x coordinate of this point with its y coordinate. That would be the equation of this angle bisector, right? And do you also see that tan theta is the slope of this chosen angle bisector? There is a point P x comma y, and if this angle is theta, this angle bisector passes through the origin, then do you realize that tan theta is going to be y minus 0 by x minus 0? Y by x is going to be the slope of this angle bisector. And what would tan theta 1 be? m1. what would tan theta 2 be? M2. Yes or no? Okay. Now, my objective is to do what? My objective is to connect the x and y coordinates of any point on the angle bisector, and which in turn would produce the equation of the angle bisector, isn't it? A relationship connecting the x and y coordinates of points on the angle bisector would be the equation of the angle bisector. That's how we have defined the equation of a line, right? So, I now do this. Tan 2 theta, which is this, is tan of theta 1 plus theta 2. Or 2 tan theta by 1 minus tan square theta is going to be tan theta 1 plus tan theta 2 divided by 1 minus tan theta 1 into tan theta 2. Right? Where what is tan theta? Tan theta is y by x. X comma y is any point on the angle bisector, right? So I replace this tan theta by y by x, where x comma y is any point on the angle bisector. And tan theta 1 by m1, tan theta 2 by m2. So this is going to become m1 plus m2 divided by 1 minus m1 m2, and m1 plus m2 I know is minus 2h by b. m1 m2 I know is a by b, right? So 2 tan theta means 2 into y by x divided by 1 minus y by x whole square, right? That's equal to m1 plus m2 by 1 minus m1 m2. m1 plus m2 is minus 2h by b divided by 1 minus m1 m2, 1 minus a by b. Yes or no? Clear? Which gives us 2 into xy divided by x squared minus y squared equals 2h divided by a minus b. See? 2h divided by a minus b, this is what I get, which is like x squared minus y squared by xy equals a minus b by h. Yes or no? Any point on any of the two angle bisectors will satisfy this equation. Any point on any of the two angle bisectors between these two lines will satisfy this condition. This then must be the combined equation of the two angle bisectors. This then must be the combined equation of the two angle bisectors between these two lines, right? Now notice, let me write it in conventional format. I end up getting h into x squared minus a minus b into xy minus h into y squared equal to 0, which is something into x squared plus something into xy plus something into y squared equal to 0, which is a homogeneous second degree equation in x and y, yes or no? Which represents what? A pair of straight lines passing through the origin, right? And coefficient of x squared plus coefficient of y squared is 0, and therefore these two lines must be mutually perpendicular, right? So this represents the pair of angle bisectors between these two lines, and as you can witness readily from here, they are mutually perpendicular. They are mutually perpendicular. This is the combined equation of the pair of angle bisectors. Combined equation of the pair of angle bisectors between The two lines represented by this. Got me? If the two lines are presented in a compact manner, why not present their angle bisectors also in a consolidated compact manner, which is this. And as expected, coefficient of x square plus coefficient of y squared is 0, causing the two angle bisectors to be perpendicular to each other. Right? So far so good, right? Now these are two lines passing through the origin. This is the combined equation of two lines passing through the origin. This was one line, y equal to m1x, and this was another line, y equal to m2x. Whose combined equation was this? Whose combined equation was this? In fact, see, the roots of this quadratic are m1 and m2. So this must have, if you factorize this, then y by x minus m1 must be a factor of this, and y by x minus m2 must be a factor of this. Yes or no? Because if I factorize this expression, then y by x minus m1 must be a factor, because y by x could be m1, right? And y by x minus m2 must also be a factor of this, because y, do you understand this? That means this expression when factorized would be this equal to 0. Okay, if there is a quadratic ax squared plus bx plus c equal to 0, and if its roots are alpha and beta, that means this expression will vanish at x equal to alpha, this expression will vanish at x equal to beta, right? So if it vanishes at x equal to alpha, that means x minus alpha must be a factor of this. Then only it will vanish at x equal to alpha, this expression. If it vanishes at x equal to beta, that means x minus beta must also be a factor of this, right? When you factorize an expression, you are actually creating an identity. So, and then a, because coefficient of x square must be equal to coefficient of x squared. See, coefficient of x square on this side is a, coefficient of x square on this side must also be a. No, you don't understand this, right? Not very sure. I'll explain again, don't worry. See, you have learned basic quadratics somewhere. Okay. If this is a quadratic expression, this is just an expression. What is it that I mean by the roots of a quadratic? Values of x for which this becomes 0. So if this has a root alpha, that means when you plug in x equal to alpha, this must become 0. That means x minus alpha must feature as a factor in this. At x equal to beta, this expression again becomes 0. Right? That means x minus, when you factorize this expression, x minus beta must be a factor in this expression. That's when at x equal to beta, it will become 0. Right? Now, when you are factorizing an expression, what are you creating? An equation or an identity? X square minus 1 is x plus 1 into x minus 1. Is it an equation or an identity? It's an identity. Factorizing is like creating an identity. If two expressions are identical, then coefficient of x square on one side will be equal to coefficient of x square on the other side. Coefficient of x power p on one side will be coefficient of x power p on the other side. Coefficient of x power London on one side will be equal to coefficient of x power London on the other side, right? So one thing, if I'm factorizing this and I have knowledge of the fact that alpha and beta are the roots of this, then what is guaranteed is that x minus alpha and x minus beta must necessarily be factors of this expression. But Why can't this be equal to this? Factorizing means not just finding factors, but also causing the two to be identical. Now, when will the two be identical? If coefficient of x on this side is equal to coefficient of x on this side, coefficient of x square on this side is equal to coefficient of x square on this side. Now, what's the coefficient of x square on this side? A. What's the coefficient of x square on this side? 1. So they are not identical. To cause them to be identical, I multiply this by a. Then the coefficient of x square on both sides will be equal. And then this becomes an identity. Now if this becomes an identity, just take a look. It's plugged, it's packaged with alpha and beta. Just check this. Alpha beta will take care of B. How? How would alpha beta take care? This is identical to this. Now if I divide by a both sides, then x square plus b by a into x plus c by a must be x minus alpha into x minus beta, must be equal to x minus alpha, dividing by a both sides, right? X minus alpha into x minus beta is what? X squared minus x into alpha plus beta plus alpha beta. Yes or no? This is identical to this. Coefficient of x square 1, coefficient of x square 1. Coefficient of x square here, x is b by a here, coefficient of x is minus of alpha plus beta here. So alpha plus beta must be minus b by a, equating coefficient of x on both sides, sum of the roots of a quadratic, right? The constant term is c by a here and is alpha beta there. So product of the roots alpha beta must be c by a. Yes or no? This is how you find the sum and product of the roots of a quadratic without having knowledge of the roots. You don't have to take recourse to saying x is minus b plus minus root b squared minus 4ac by 2 add and alpha plus beta is this. No, you don't need to know the roots to find the sum and product of the roots, right? See, you could just factorize it like this and equate coefficients of equal powers of x on both sides to get the sum and product of the roots of a quadratic. Got me? Sure. Pakka. Okay. So now that's exactly what I did. Look at this. This is a quadratic in y by x. And it has one of the roots as m1. So y by x minus m1 must be a factor. One of the roots will be m2. So y by x minus m2 must be a factor. But this can't be identical to this. Why? Because coefficient of y by x whole squared here is b. And coefficient of y by x whole squared is 1 here. So then, to bring about parity, I multiply by b both sides. This is what transpires. Giving me b into y by x minus m1 into y by x minus m2 equal to 0, causing y by x to be m1 or y by x to be m2, which means y equal to m1x or y equal to m2x, causing this to represent a pair of straight lines. Right? Combined equation of these two lines. All's fine. Can I remove the clutter from here? You were not aware of the fact how to find the sum and product of the roots of a quadratic? You knew this, or you found minus b plus minus root b squared minus 4ac by 2a. Sridharacharya. Huh? Sridharacharya is what you knew. Where? There is, okay, what did they teach you in class 10? My good old teacher taught me this. My good old teacher taught me this only. If your teacher didn't teach you that, it's not a problem of the system, it's a problem with the teacher. Alright? So if I took some classes for these kids in class 10, I would teach this only. So it depends on who's teaching. Right? Got it? Worried? No. You should be. Can I wipe this off? Now, coming back to the problem that I was aiming at addressing. These are the two lines represented by this homogeneous second degree equation in x and y. Clear? Where m1 and m2 are the roots of this quadratic in y by x. Now suppose there is some point P, x1, y1. There is some point P, x1, y1. From P I can drop a perpendicular on one of the lines, call it PA. Yes or no? From P I can drop a perpendicular on the other line, call it PB. Given a point x1, y1 and given a pair of straight lines like this, real straight lines I mean, given a pair of straight lines like this and given a point P x1, y1 like this, right? I now want to find the product of the perpendiculars from P onto the two lines. I want to do this. PA into PB is what I want to find. Given x1, y1 and given this. m1 and m2 I am only imagining that I know, right? But I am not getting into the mess of obtaining m1 and m2 exclusively, right? Right? So all that I am consuming is x1, y1 and the fact that there is a pair of lines like this. And what is it that I am trying to find? I am trying to find and obtain the product of the perpendiculars from the point P onto the two lines. That means PA into PB. I want to give you around 10 minutes to ponder over it. See if you can give me a result. I will also get you started. What you might want to do is, say PA for example. The perpendicular distance of P from this line, that means from m1x minus y equal to 0 is this line. And how do you find the perpendicular distance of x1, y1 from this line? x1, y1 mod of this divided by root m1 squared plus 1, right? So PA is what? PA is mod of m1 x1 minus y1, right? Divided by root 1 plus m1 squared, perpendicular distance of a point from a line, right? What is PB? Similarly, m2 x1 minus y1 divided by root 1 plus m2 squared. Yes or no? Now I want you to find the product PA into PB, and once you find this product, I want x1, y1 to stick around, but I don't want m1 and m2 to stick around because I only pretended that I know m1 and m2, right? But I actually don't know m1 and m2. I can solve for m1 and m2 very laboriously, but I don't want to use that. I want to eliminate m1 and m2 using these two. You know what I'm saying? So all of you then get on with the business of simplifying PA into PB, multiply these two, eliminate m1 and m2 with these two, right? Almost all of you have got this right, PA into PB. What transpires here is this PA into PB. When I multiply this with this will then turn out to be this into this. See? m1 m2 into x squared minus m1 plus m2 into x1 y1 plus y1 squared. That's a numerator when you multiply. Am I right? Yes or no? If you multiply these two, see m1 m2 x1 squared and then x1 y1 minus m1 minus x1 y1 minus m2, which is this term, and then y1 squared, which is this term, right? And then multiply the denominators. The denominators would be 1 plus m1 squared plus m2 squared plus m1 squared m2 squared. When the denominators are multiplied, this is what transpires, right? So that's PA into PB. Now, evidently, all that you need to do here is, this m1, m2 is already known to us, So PA into PB is mod of M1 M2, which is A by B into x1 squared, which is this term, and then M1 plus M2 is going to be minus 2h by b, so plus 2h by b into x1 y1 plus y1 squared, which will not be tinkered with, this, and then this part is like 1 plus m1 squared plus m2 squared is what? M1 plus m2 whole squared minus 2 m1 m2 plus m1 squared m2 squared. That's inside the square root, right? So then the denominator would turn out to be 1 plus m1 plus m2 whole squared, which is 4h squared by b squared, minus 2 m1 m2, that means minus 2a by b, and then m1 squared m2 squared. This is m1 squared m2 squared, which is a squared by b squared, right? Clearly then, multiplying both numerator denominator by say b, this b will become like a x1 squared plus 2h x1 y1 plus b y1 squared, multiplying, and then this will become, there is a root b squared which will cancel with this b, and this will become inside the square root 4h squared plus a minus b whole squared, as all of you have got independently as well. And of course the modulus, this is what it would become. I can see that you were all at it and you got this right. Very good. So that's another result I want you to take cognizance of. I want you to remember this result. Right? Given a pair of lines, how to find the product of the perpendiculars from a point P x1 y1 onto a line? Replace x by x1, y by y1, take the modulus and divide by root a minus b whole squared plus 4h squared. That will give you the product of the perpendiculars from x1 y1 to the two lines represented by this. Got me? Now, can I wipe this off? Now, if I had something like, so what did this give me? This gave me ax squared plus 2hxy plus by squared equal to 0. Gave me a pair of lines passing through the origin, right? This gave me a pair of straight lines passing through the origin. One of slope m1, the other one of slope m2. This is what I got out of this, right? Suppose I had something like this, and this was homogeneous second degree equation in x and y, offering to me a pair of straight lines passing through the origin. Real lines if h squared was greater than or equal to ab, right? Suppose I had something like this, a into x minus alpha whole square plus 2h into x minus alpha into y minus beta plus b into y minus beta whole square equal to 0. Suppose I had an entity like this. This, under no circumstances, is a homogeneous second degree equation in x and y. Because see, I have terms which are, for example, b into beta squared, which is not a second degree term. If you expand this, not all terms here would be second degree terms. The algebraic sum of the powers of x and y will not add up to 2, right? See, some terms are second degree. Ax squared is a second degree term. 2hxy is a second degree term. By squared is a second degree term. All of the terms are not second degree. There are degree 1 terms. For example, minus 2b into beta into y is a degree 1 term. Then minus 2h x into minus beta is a degree 1 term. 2h minus alpha into y is a degree 1 term. Then minus 2x into alpha is a degree 1 term. There are degree 0 terms here also. A alpha squared, for example. The sum of the powers of x and y add up to 0 there. That's degree 0 term. That's a constant term, right? Then 2h alpha beta is degree 0 term. Sum of the powers of x and y add up to 0. Then b into beta squared. That's a degree 0 term. Yes or no? Right? So this is not homogeneous second degree in x and y. This is not homogeneous second degree in x and y. Here you have degree 2 terms, you have degree 1 term and degree 0 terms. Right? 2h alpha beta x power 0 into y power 0. That's how you can write this, isn't it? So 0 plus 0, 0 plus 0, approximately 0. Right? No? Good. So now let me address this. What on earth will this represent? Very good. Yes, you're right. Absolutely. You are yourself shocked? I was also shocked, but you seem to be more shocked that you are right. I was a little shocked, but not that shocked. Yes, but let's understand why. One thing for sure, whatever this represents, see, this will pass through alpha comma beta, isn't it? Put x equal to alpha, y equal to beta, this is indeed going to be 0. That means whatever this represents, whatever geometrical entity it seems to represent, that will pass through alpha beta. So this certainly is a curve passing through alpha beta. Like this is a curve passing through 0, 0. This will be a curve passing through alpha comma beta. That's for sure. Yes. But then, little more to it than this. Now what I do is, I divide both sides by x minus alpha whole squared. I divide both sides by x minus alpha whole squared. So starting from the third term, b into y minus beta by x minus alpha whole square, right? Plus 2h into y minus beta by x minus alpha, right? That's the second term. This one on dividing by x minus alpha whole square. And then this term is a equal to 0. This is what I get. Yes or no? In the earlier case, on dividing by x square, this gave me a quadratic in y by x. This gave me a quadratic in y by x, whereas this is giving me a quadratic in y minus beta by x minus alpha. Yes or no? This gives me a quadratic in y minus beta by x minus alpha. This gives me a quadratic in y minus beta by x minus alpha. Is that all right or not all right? Right? So when I solve for this quadratic in y minus beta by x minus alpha, then I'll get two values of y minus beta by x minus alpha. Y minus beta is m1 and y minus beta by x minus alpha could be m1 or it could be m2. Yes or no? Y minus beta by x minus alpha could be m1 or it could be m2. Right? Now, y minus beta by x minus alpha equal to m1, for example. Where what are m1? What is m1 and m2? m1 and m2 are roots of this quadratic. Right? Like before, m1 plus m2 is going to be minus 2h by b? Yes or no? M1, M2, the product of the roots of this quadratic is going to be a by b. Yes or no? When you solve for y minus beta by x minus alpha, two values will pop out. One would be y minus beta by x minus alpha could be m1 or it could be m2. m1 or m2. So m1 plus m2 would be minus 2h by b, and m1, m2 is going to be a by b. Yes or no? Now, say y minus beta by x minus alpha equal to m1 is one of the outcomes of this. That means one of the outcomes of this. What is this? Realize that this represents a line passing through alpha beta having slope m equal to m1. Having slope m equal to n1. Isn't it? What's the equation of a line passing through alpha beta having slope m1? This is the equation of the line, isn't it? For example, if you took any point xy on the line, then what would be the equation of this line? Y minus beta by x minus alpha equal to the slope m1 for any xy lying on the line. For any xy lying on the line. Yes or no? So this represents a line passing through alpha beta with slope m1. Isn't it? This represents a line passing through alpha beta with slope m1. Yes or no? So of the two things that this represents, one is a line passing through alpha beta and with slope m equal to m1. Where what are m1 and m2? m1 and m2 are the roots of this quadratic. m1 plus m2 is going to be minus 2h by b. m1 m2 is going to be a by b as suggested. Confusing you? No? No? So now y by x minus y by n is beta by x minus alpha could also be m2. Could also be m2. And what would this represent? This would also represent a line passing through alpha beta but with slope m2. So this would represent a line with slope m equal to m2 and passing through a point P alpha comma beta. Yes or no? So together, what does this represent? A pair of lines passing through alpha beta, that means intersecting at alpha beta, one with slope m1, the other one with slope m2, where m1 plus m2 is minus 2h by b, m1 m2 is a by b. Yes or no? Got me? Right? So far so good, right? So what transpires then very simply is, like this represents a pair of straight lines passing through the origin with slope m1 and m2. This represents a pair of lines passing through alpha beta but with slope m1 and m2. The second one, this is 1 and this is 2, the second case. Yes or no? So what's the geometric representation of this? This represents a pair of lines passing through the origin, passing through alpha beta with slopes m1 and m2, where m1 plus m2 is minus 2h by b, m1 m2 is a by b. What does this represent? A pair of straight lines passing through the origin with slope m1 and m2, where m1 plus m2, like before, is minus 2h by b and m1 m2 is a by b. Okay, now in this case, again, in order that the two lines are real, m1 and m2 would have to be real. That means the discriminant would have to be greater than 0, greater than or equal to 0. Again, the condition for the two lines represented by this and therefore by this to be real is that h squared must be greater than or equal to ab. That's when these two lines would be real. That's when these two lines would be real. Yes or no? What's the discriminant to this? 4h squared minus 4ab. That greater than or equal to 0 would mean h squared greater than or equal to ab will cause the two lines represented by this and therefore by this to be real. What's the condition for the two lines here to be real? Same thing. H squared greater than or equal to ab. Yes or no? Please listen to me very carefully. I hope you are in sync with me and you are being able to register all that I am saying so far. Right? Now, the two lines represented by this have slopes m1 and m2 given by this. The two lines represented by this have slopes m1 and m2 given by this. Tell me, the slopes of the two lines here, is it the same as the slopes of the two lines there? When you solve for y by x here, and you solve for y minus beta by x minus alpha here, will you not get the same values? Huh? Or look at the slopes of this. m1 plus m2 is this, m1 m2 is this. Look at the slopes of the two lines here. Same m1 plus m2 and same m1 m2. That means m1 and m2 obtained from these two will be the same as m1 and m2 obtained from these two. That means this pair of lines is perpendicular to this pair. Yes or no? That means the two lines represented by this are these. One with slope m1, one with slope m2. The two lines, the pair of lines represented by this will be parallel to this pair. This line parallel to this line parallel to this line. That means, and both have the same condition for the two lines to be real. H squared greater than or equal to AB. Right? Angel, got me? That means this equation and this equation, they have something in common. Both represent pair of lines. This one represents a pair of straight lines passing through the origin, whereas this represents a pair of straight lines passing through alpha beta. But the pair here will be parallel to the pair there. It's as if this pair is given and you shift this entire thing to alpha beta, this point O to alpha beta, then you get this pair. This is what transpires really. You know what I'm saying? Is some known point. Alpha beta is some known point. Right? Alpha beta is a fixed entity. So this represents a pair of straight lines passing through some alpha beta known to be. This represents a pair of straight lines passing through the origin. But this pair will be parallel to the other pair. The only difference is that this pair intersects at 0, 0, this pair intersects at alpha beta. Right? But they will be respectively parallel to the corresponding lines. Right? Is that okay or not okay? Now, so can I just for a moment remove the clutter from here?
So can we say that they represent the opposite points of a parallelogram? Like
Opposite points?
opposite vertices.
There is no parallelogram. These are lines infinitely stretching.
If we extend, it forms a parallelogram.
I mean, yes, what do you extend? What do you extend? What, you mean this line and this line? Yeah, then they will form a parallelogram. You mean I do this, and I do this. Then there will be a parallelogram, isn't it? What you are saying is essentially this. Then this is the parallelogram. Yeah, of course.
No, what I'm saying that the opposite vertices will be the
Oh, these 0, 0 and alpha beta. That means this will be the diagonal of that parallelogram. One of the diagonals. Yeah, absolutely. The diagonal passes through the origin. Yeah. Okay, good. Very good. Nice thought. Right. Shall I proceed? Now, my point of contention is the following. Okay. I'm assuming that you have registered all of this comfortably. Clear? I'm just drawing a simile and a comparison between these two. Look, this essentially, has terms of the following kind. Ax squared plus 2hxy plus by squared plus something into x plus something into y plus something equal to 0 is what this represents. Yes or no? Okay, one more thing. And therefore, since if they are respectively parallel, this angle theta, angle between these two lines will be the same as the angle between these two lines. So if I have computed the angle between the two lines represented by this, tan theta, did I do that earlier? What was this tan theta that I obtained for this pair of lines? That was 2 root h squared minus ab divided by mod of a plus b. Right. The two lines represented by this will have the same slope, so will have the same tan theta. That means if I obtain the angle between the two lines here, then that will be the same as the angle between the two lines here, because they are respectively parallel, right? Now, what is the format of this pair of lines? Populate the second degree terms, ax squared, which is this, 2hxy, which is this. I'm just collecting the second degree terms, and by squared, which is this. And then there would be like something into x, something into y, and then some constant terms. The constant terms are a alpha squared plus 2h alpha beta plus b beta squared with feature here, right? Not all terms are second degree terms in this. These are second degree terms. These two are degree 1 terms. This is degree 0 term. So this is not a homogeneous equation in x and y, whereas this is a homogeneous equation in x and y. So now one thing, if somebody gave you a non-homogeneous equation in x and y, this is a non-homogeneous second degree equation in x and y, and you had to find, and it is known that this represented a pair of straight lines, then what you do is, in order to, instead of dealing with all the terms, just populate the second degree terms. Filter them out. These second degree terms would constitute a pair of lines that will be parallel to the pair of lines constituted by this. So then if you have to find the angle between the two lines represented by this, just filter out the second degree terms from this and find the angle between the pair of lines represented by this. That will be the same as the angle between the pair of lines represented by this. So all that you need to do is, in a generalized second degree equation in x and y, which is known to represent a pair of straight lines, to find the angle between the two lines represented by this, filter out the second degree terms, find the angle between the two lines represented by the second degree terms, homogeneous second degree terms, this, and that's going to be the same as the angle between the two lines represented by this. What's the only difference between this and this? The two lines here would intersect at the origin, whereas the two lines here would intersect at some other point, alpha comma beta. But the pair here would be parallel to the pair there. Is the idea clear or not? Make sense? A small remark on quadratic expressions, for example. See, if there is a quadratic expression, ax squared plus bx plus c, if it becomes 0 at alpha and beta, then like I told you, x minus alpha is going to be a factor of this, x minus beta is also going to be a factor of this. That means this can be written as some a into, this is an identity. When I factorize it, I am essentially creating an identity, x minus alpha into x minus beta, which is an identity, right? Now, if I want this expression to be a perfect square, this expression may not be a perfect square. See, for example, 2x plus 1 whole squared, this is a perfect square. See, 4x squared plus 4x plus 1. That's a perfect square, right? But not all quadratic expressions would be perfect squares. X minus 2 and x squared minus 5x plus 6, which is like x minus 2 into x minus 3. This is not a perfect square, right? Some quadratic expressions will be perfect squares. Some quadratic expressions will not be perfect square. This is not a perfect square, whereas 4x squared plus 4x plus 1 is a perfect square, right? Now, the condition so that this quadratic expression is a perfect square is that alpha must be equal to beta. If alpha turns out to be beta, then this expression becomes a perfect square. It becomes like a a into x minus alpha whole square. For a quadratic expression to be a perfect square, its two roots must be equal. Alpha must be equal to beta. That is when it becomes a perfect square. And when is alpha equal to beta? When the discriminant of the expression is 0. That means if b squared minus 4ac is 0. That's when the quadratic expression is rendered a perfect square. Right? So if there is a quadratic expression, the condition that will cause it to be a perfect square is what? Its discriminant must be equal to 0. Its discriminant must be equal to 0. Now, right? See, this expression ax squared plus 2hxy plus by squared plus 2gx plus 2fy plus c is not a homogeneous second degree expression in x and y. This is called a generalized second degree expression in x and y. This is a generalized second degree expression. This is a generalized second degree expression in x and y. And this equal to 0 will represent a generalized second degree equation in x and y. It's not homogeneous. It's not homogeneous. This is a second degree term. Powers of x and y are up to 2. This is a second degree term. This is a second degree term. This is degree 1. This is degree. This is degree 0. So the terms here are heterogeneous. There are degree 2 terms. There is degree 1. There are degree 1 terms. There is degree 0 term. Right? So it's a generalized second degree equation in x and y. See, if these three terms were to be 0, it will become a special case. It will become a homogeneous second degree equation in x and y. Right? Now, all the coordinate geometry that we are going to learn, would be about this generalized second degree equation in x and y. These coefficients a, h, b, f, c, etc. will enjoy different relationships based on the connectivity across these coefficients a, h, b, g, f, c. It could represent various entities that we are going to learn in plane coordinate geometry, right? This, under certain circumstances, can represent a pair of straight lines. This, under certain circumstances, will represent a circle. We learn. Under certain circumstances, it will represent a parabola, an ellipse, a hyperbola. This then is the generalized hub for all the coordinate geometry that we are seeking to learn down the line. For the time being, let me tell you that this, under certain set of conditions, not always, this under certain set of conditions can also represent a pair of straight lines. But not always. Sometimes it will represent a pair of straight lines. Sometimes it will represent a circle, ellipse, hyperbola, parabola, and sometimes it will represent nothing. That also, it will also represent a null set sometimes, right? Now, the focus in this session is to be able to obtain the condition, so that this represents a pair of straight lines. I want to find the condition, switch it off. I want to find the condition so that this represents a pair of straight lines, right? Now, say, again, going from first principles. This will represent a pair of straight lines. This will represent a pair of straight lines if I could factorize this expression into two linear expressions in x and y. You know what I'm saying? If I could factorize this into two linear expressions, Lx plus my plus n into L prime x plus m prime y plus n prime. If this could be factorized into two linear expressions in x and y, then this will represent a pair of straight lines. What are the two lines that this represents? This represents one of the lines is going to be Lx plus my plus n equal to 0. This equal to 0 is one of the lines that this will represent, and this equal to 0 would be the other line that it represents. That means L prime x plus m prime y plus n prime equal to 0 would be the other line that this represents. So this, under a certain set of conditions, can be factorized into two linear factors in x and y, isn't it? This is one linear expression in x and y. This is another linear expression in x and y. Under certain set of conditions, which is what we want to investigate, this could be factorized into two linear expressions in x and y. If that can happen, then this is capable of representing a pair of straight lines. This equal to 0, that is this would be one of the lines, or this equal to 0 will give me the other line. So what am I trying to do here? Find the condition so that this represents a pair of straight lines. That means find the condition so that this could be factored into two linear expressions in x and y. Clear? Now, essentially then, if I solve for y here, then what are the two values of y that if suppose it could be factorized into two linear expressions in x and y. Do you realize I could write this as a quadratic in y, and I can solve for y in terms of x, isn't it? Can I not write this as a quadratic in y? By squared plus y into 2f plus 2hx plus ax squared plus 2gx plus c. It could be written as a quadratic in y. And when I solve for y, what should be the two values of y that should be obtained here? One of the values of y would be minus of Lx plus n by m. That should be one of the values of y when I solve for y from this, isn't it? What value of y will you get from this? This equal to 0 will give me y equal to minus of Lx plus n by m. The other value of y that I should get when I solve for y from this quadratic is going to be minus of the y obtained from this must be minus of L prime x plus n prime by m prime. These are the two values of y that I should get. Essentially then, the values of y obtained from this are linear expressions in x, right? So what I seek to get is, when I solve for y from here, y should be a linear in x. Y should be a linear expression in x. Y should be a linear expression in x. That means if y can be written as a linear expression in x, then this could be factorized into two linear expressions in x and y, and this then becomes potentially capable of representing a pair of straight lines. Do you understand the equivalent problem? The equivalent problem is, if y could be expressed as a linear in x from this equation, then this will represent, this could be factorized into two linear factors in x and y, and therefore is capable of representing a pair of straight lines. Right? Very good. Now, let me write this with y becoming my subject. By squared plus 2 into hx plus f into y plus 2gx plus ax squared plus c. Let me just write this. Ax squared plus 2gx plus c equal to 0. Do you realize whatever I have done here? Does it make sense to all of you? You know what have I done here? I have collected terms, by squared, and then I have collected this term, and I have taken 2y common, so I end up getting hx plus f. And then other terms which do not contain y are ax square plus 2gx plus c. This is what transpires. So it's like something into y squared plus something into y plus something that does not contain y equal to 0 is a quadratic in y. Now when I solve for y, what should I get so that it can represent a pair of straight lines? Y should be a linear in x. Right? Okay, let me solve for y using Sridharacharya. It's a quadratic in y. I can solve for y using Sridharacharya. Y then is going to be minus of 2 hx plus f plus minus 2 root hx plus f whole squared minus b into ax squared plus 2gx plus c divided by 2b, or not to be. To be, right? Minus of b plus minus root this square minus 4 times b into this. That 4 comes out as 2 divided by 2 times a. A is b here. Clear? Solving for y using Sridharacharya, right? Now, this 2 of course goes into oblivion. I want y to be a linear in x, essentially. See, don't lose focus. I want y to be a linear in x. If y turns out to be a linear in x, then this could be factorized into 2 linear expressions in x and y, and therefore represents a pair of straight lines. Okay. Now, this anyways is a linear in x. So I want square root of this to also be a linear in x, so that sum or difference of 2 linears is also a linear in x. Right? So then, for this whole thing to be a linear in x, this should be a linear in x. This should be a linear in x. That means root hx plus f whole square, this quantity, this should be a linear in x, square root of this, minus b into ax squared plus 2gx plus c. That must be a linear in x. That must be a linear in x. Right? If it's a linear in x, that means it must be of the form some px plus q. It must be of the form px plus q. Right? If it's a linear in x, this is a linear in x, then it must be of the form some px plus q. Right? So far so good, right? That means hx plus f whole squared minus b into ax squared plus 2gx plus c must be some px plus q whole squared. Squaring both sides. Right? Squaring this, square of this. That means this expression must be a perfect square. This must be a perfect square. This is what it means. This must be a perfect square. This is what it means. Right? This, notice, is like h squared minus ab, h squared minus ab into x squared. See, h squared minus ab into x squared plus x into hf minus 2bg, right? See, the middle term of this, 2x into hf, and the term minus 2gb into x, right? Plus f squared minus bc. This is what it is. This must be a perfect square. Okay, right, right. Is that okay? This has to be a perfect square. This is a quadratic in x. When would a quadratic be a perfect square? If the discriminant is equal to 0. If the discriminant is equal to 0. For this to be a perfect square, its discriminant must be equal to 0. That means 4 into hf minus bg whole squared minus h squared minus ab into f squared minus bc must be equal to 0. This is what must result.
Before it should be the 2 because b is 2 into that.
What?
So the 2 should go inside 2hf minus 2b.
Because b, the second term is n.
Yeah, I've taken 2 common.
That's a square. b square. This 2 becomes a 4.
B square 4, this squared minus 4, this into this. That must be equal to 0. Clear? See, the next thing I would just keep in a black box. This h square, f square, h square, f square would get cancelled. If you simplify this with some algebraic manipulation, the final result, let me tell you, of this simplification, without getting into too much of computation at this stage, the final result that corresponds to this condition. So this then is the condition that this will represent a pair of straight lines. Right? This is the condition so that this represents a pair of straight lines. Am I right? This, when simplified, let me tell you the final cosmetic version of this. When simplified, it will turn out to be the following. It will be the following determinant. This determinant equal to 0 is really what this will represent. This then will be the condition so that this represents a pair of straight lines. Realize how you can do is, see, look at the second degree terms, or look at these terms, A, B and C. They will constitute the diagonals, AHG, AHG. The first row and the first column would be AHG, AHG. Then the other two elements will be F. So the diagonal will be ABC. A is coefficient of x square, B is coefficient of y squared, C is the constant term. That will constitute the diagonal of this determinant. And then H and G, the first row and the first column will be AHG, AHG, AHG. Where what is H? H is half the coefficient of xy. H is half the coefficient of xy, isn't it? AHG. G is half the coefficient of x. G is half the coefficient of x. And then F and F will constitute the remaining two entries in this determinant. This equal to 0 is the condition so that this represents a pair of straight lines. Under other conditions, it could represent a circle, a parabola, ellipse, hyperbola, but then this will cause the generalized second degree equation in x and y to represent a pair of straight lines. this could be factored into two linear factors in x and y, provided this determinant is equal to 0. This is the condition for which the equation represents a pair of straight lines. Two more remarks in connection with this. So if this is 0, then we know that this represents a pair of straight lines. Let me know if I could wipe this off. So you have to remember this. You have to remember this. Now, once that determinant is 0, you are convinced that this will represent a pair of straight lines. But this is not a pair of straight lines that intersect at origin. This would be a pair of straight lines that intersect at some alpha beta. This would be a pair of straight lines that will intersect at some point alpha beta. One of the lines will have slope m1, the other one would have slope m2. Now, if I have to find the angle between the two lines represented by this, what I do is, I filter out the second degree terms from this. The second degree terms are ax squared plus 2hxy plus by squared equal to 0 is a homogeneous second degree curve. And what does this represent? This will represent a pair of straight lines passing through the origin. But this pair of straight lines and this pair of straight lines will be respectively parallel to each other, like I mentioned previously, right? So if this has slope m1 and m2, this pair will also have slope m1 and m2, and therefore the angle between this pair is the same as the angle between this pair, right? And the angle between this pair I have already found. The angle between this pair is tan theta equal to 2 root h squared minus ab by mod of a plus b, and that's going to be the same as the tan of the angle between the two pairs represented by this, right? If someone insists that you find the angle between two lines, then forget everything else, just populate the second degree terms. Find the angle between the two lines represented by this. That will be the same as the angle between the two lines represented by this. Got me? Now the question is, how do you find the point of intersection of these two lines given this format? In the earlier format where, I served everything to you on a platter, I said a into x minus alpha whole squared plus 2h into x minus alpha into y minus beta plus b into y minus beta whole squared equal to 0. Then of course it was so easy to see that the point of intersection was alpha beta. But now when presented in this format, how does one find the point of intersection alpha beta of the two lines? Now, a result which I am going to tell you right now, but will not divulge further than the final result, at least for this point of time, until and unless you mature a little more. The point of intersection alpha beta between the two lines, if it actually represents a pair of straight lines, is going to be given by the following. How does one find alpha beta? Call this expression as a function of x and y, which is x and y, which is like ax squared plus 2hxy plus by squared 2gx 2fy plus c. Call this expression f of xy. Now, what is it that I'm trying to do? I'm trying to find the point of intersection between the two lines represented by this, if it at all does. Differentiate f with respect to x. This is called differentiating f with respect to x, keeping y constant. This is called partial differentiation. This is called partial differentiation, dou f dou x. That means, assume as if y is constant and you are differentiating this with respect to x. What would you get? 2ax from this, keeping y constant, 2hy, 0, I am assuming y is constant, 0, 2g, 0, 0, okay, and equated to 0, differentiate with respect to x as if y is constant and equated to 0. That's equation 1. Similarly, differentiate f with respect to y, keeping x constant. Differentiate f with respect to y, keeping x constant. What would you get? 0, 0, x constant. 2, h. Differentiate with respect to y. So 2hx, 2by, 0, 2f, and equated to 0. That's second equation. Now you have a pair of simultaneous equations in x and y. You have a pair of simultaneous equations in x and y. Solve this pair. Solve for x and y from these two equations. xy from these two equations. And that will be the same as alpha beta. The x that you obtained by solving these two would be alpha. The y that you obtained by solving these two would be beta. And this alpha beta would be the point of intersection of the two lines represented by this, provided it actually represents a pair of straight lines. When would it represent a pair of straight lines? If that determinant is equal to 0. So now once that determinant is 0, you can find the angle between the two lines represented by this by simply isolating the second degree terms. How do you find the point of intersection of the two lines represented by this? Differentiate this expression with respect to x, keeping y constant, equated to 0. Differentiate this with respect to y, keeping x constant, equated to 0. Solve this pair of equations for x and y, simultaneous equations. Then the xy that you obtain would be the point of intersection alpha beta of the two lines that this represents. Got me? All's good?